Not much of this is examinable in this year's paper. So just stay with me and try to highlight the areas that I'll be stressing on, okay? I'll go through the objectives. This is different to the one of the earlier course outline I had sent you, all right? So basically this is specific to the class today in terms of what we want to try to go through, all right? You see there, you'll learn a little bit about, we'll talk a little bit about seismic derived velocities. And what that means essentially is you'll understand things like how velocities are important in processing. Remember when last day we spoke about normal move out correction, which is a time shift. Okay, what you're trying to do is flatten the girders. Remember that? Those diagrams?
Yes, sir.
Yes,
Right.
sir.
Yeah.
So basically what you are getting out of that process in terms of NMO correction and flattening of girders and so on, you are getting the migration velocities that goes into the processing. That is very, very important because it allows you to put things in the correct place. And that is the whole idea behind seismic migration. Okay, but there are other types of velocities that are important, but we won't spend too much time on it, as I mentioned. Those types of velocities are like what we call RMS velocities, root mean square velocities, interval velocities, average velocities, to go alongside the migration and stacking velocities. So when you hear migration velocities, it's the same as basically stacking velocities. In your final year, you will go through some of those concepts in more detail, I believe. Okay, we'll talk a little bit about what is a synthetic seismogram and the usefulness of it, and its application in what is called the well tie process. Okay? Remember now we have already acquired the data, we have processed the data, now we are ready to utilize the information. So most of your final year projects, you would be essentially undertaking a lot of seismic interpretation work. Most of you, some of you all decide to do paleontology and things, but the other reports are typically seismic interpretation. All right. Then we have why you depth convert, and remember seismic data is recorded in time, and you need to get that time into depth. Okay, which is where you can plan your wells and plan your casing and all the different things that go along with drilling the well. All right. We'll talk a little bit about 2D and 3D seismic interpretation. And then from 3.6 onwards is basically the add-ons, which are things like seismic attributes, seismic inversion, AVO, which is amplitude versus offset. All of these are under the heading of quantitative interpretation. So what you're doing is basically using some equations and values to help you ascertain the reservoir characteristics. Okay, you're trying to understand what the seismic data is telling you, right? It's not only just colors, red, white, and black, or red, white, and blue. Some of the color scales that they use in seismic, in viewing seismic. But you're really trying to understand what the wiggle waveform is telling you. All right, stop me if you have questions and stuff. Then we'll talk about briefly I'll just give you a note on direct hydrocarbon indicators. It's a concept I normally test every year, It's not being examinable this year. How to tie now your reserves estimation and understanding a little bit about the process of maps and montages and the approval process, really, in terms of drilling, drilling on location, all right, which is the whole aim behind spending all this money, is in terms of acquisition, processing, and interpretation. All right, so let's go. So what is the primary goal of seismic interpretation? You all know this, but just for your review, it's basically to describe the reservoir that is supported by the geophysics and the geology, and understanding some of the subsurface structure and stratigraphy. So essentially, what you want to do is map your faults, map your surfaces of interest, and see what those structures are really telling you. Whether the structure whether the reservoir, whatever form it might take, it might be an anticlinal feature, it might be a unconformity trap, it could be a stratigraphic trap, it could be a tilted fault block, all different types of traps that hydrocarbons are essentially in. Okay, so that's basically the goal of seismic interpretation. All right, so we'll go through in the next couple of slides what a typical seismic interpretation workflow is. And you can use this as a guide. It's not cast in stone, but these are some of the things that you'll be doing. You need to have an understanding of the geology, of course. As you know by now from your 2 years in the program, you must have an understanding of the structural setting, whether it's an extensional regime, compressional regime, a salt shale regime, a thrust fault system. Okay, you must have an understanding of the stratigraphic setting. I think you have a good foundation now for you to put into context what the structure and what the stratigraphy is telling you. Okay, more so as it pertains to Trinidad geology. Okay, both North Coast, East Coast, and the Western Peninsula. You will have to do some sort of seismic data assessment. So you just don't dive straight into the interpretation. You must understand some of the acquisition, because when you start in a company, more likely or not, they will already have data at your disposal, right? So you will have to go back and do some read up on how the data was acquired, how the data was processed, what are some shortcomings of the data, whether data is of sufficient quality for you to undertake an interpretation in the onset. And this is assuming that you have data, seismic data. Yeah? You might be doing an interpretation where you don't have seismic data. You just have well information. Okay? And that is where your correlations and marker, your understanding of your stratigraphy and so on are very, very important. Just a minute. Yes, Yana? Well, why are you chewing gum? I'll check my bag. Sorry about that. Yeah. So, in terms of the processing, you need to have some understanding of the noise, the frequency, bandwidth. So, any near surface problems, and if you can do any interim corrections to the data, right at your workstation, some of the things that you may be able to do, and some of the things that you might have to send back to the shop to get some enhancement. All right? You must have an understanding of your velocities, and the velocities are very important in the time to depth conversion, because if you understand the triangular formula, which is your velocity is your depth over time, right? you need to have that sort of three-way relationship. So velocities are important in that time to depth conversion. The third step, develop a well to seismic tie. So you need to have a control well, usually a well that has good well log information, typically a gamma, resistivity, caliper, sonic data, density are the key ones. All right, and why am I asking if you have density and sonic data? You think what will that allow you to get? We haven't reached the quantifying part of it, but in terms of the density log and the acoustic log, what log can we get from that when you sum them? You get the acoustic impedance log, no sir? Remember?
Yeah.
The product of the velocity and the density? Right, and from the AI log, you can also get the reflectivity series, which you can create a wavelet out of the well logs. And you can use that wavelet now to compare it to your seismic data. And that is the whole well to seismic tie. That is that whole process. Okay? We'll talk about that in the body of the lecture. Then you have to come up with an interpretation strategy. And that strategy is dictated by the software that you are using. Okay? You might be using Landmark, Decision Space. Have you heard about Decision Space?
No.
Huh? Well, Decision Space is the present software package from Halliburton, from Landmark. Right in when you walk through your door there in Jerusalem, you'll see that big poster. Well, Landmark is really Halliburton, right? And the software interpretation package is really the new version now is Decision Space. It was previously OpenWorks, where you had SizeWorks and StratWorks and so on. SizeWorks is the interpretation software. This girl want to see you all here, and then she will go back upstairs. Come quick, Sian. Come fast, come. Come and say hello and go upstairs and do your work. Come. See this here. Say hello. Quickly.
Hi. Hi.
Right, you're following us now. So. Hi and bye. All right. Good. So we got, I have to babysit again today. So. Right, so the interpretation strategy it is dictated by the software. So Decision Space is one, Petrel is another. Some of you might be using Petrel. Open Detect. Remember I told you that we're supposed to do as exercise. We didn't get around to that part. But Open Detect is a free software. You have there are many others. Some of the Paradigm and a lot of other proprietary software available in the market, right? But the good ones are essentially Petrel and Decision Space right now. Then you have to do some sort of attribute analysis where you put some sort of relationship to what you can get out of the seismic data and try to form a relationship with the attribute itself and geology. And then the rest of the things are really semantics. 6 to 10, basically, that is where you're just doing like report writing, understanding what you did now and trying to ascertain areas to drill, how much reserves you have in place, more things that the manager will be really interested in. Okay, from 6 to 10. That's just that's the business side of things, I should say. All right, but like from 1 to 6, essentially, 1 to 5, sorry, what you as a geoscientist really and truly is responsible for in the first instance, and then the other things are just add-ons or additional things that you need to be able to do as well. So you put some of your engineering that you learn to bear, understand if you have reserves available, where would you position your well and generate an FTP for your manager, all right? Why are we not moving? Okay, so a simple interpretation strategy, you obviously have to have some understanding of the data. So you do a quick scan, you understand the best wells in your area, right? You have to understand the aerial extent of your area that needs interpretation or needs interpreting, the key horizons, and the horizons are really derived from your formation tops or your bio or your stratigraphic markers, all right? And it's very straightforward, very simple. You build an interpretation framework where the area is, where the data quality is good, and then you move outwards into the bad areas. To the edges of the data set, typically data deteriorates. All right, so you want to build your interpretation framework in the good data, in the good areas, and then move out. And then you could also do some what they call post-processing techniques. You could play around with the toolkit that is available to you in your software package and see if you can enhance some of the seismic, all right, for interpretation purposes. Sometimes you can enhance and deteriorate, or not deteriorate, but bring the data to a limit where you can't do anything more with it, really and truly. All right, so it's really for visual purposes and for interpretation purposes. Some people start with default and interpreting default. Some people start with the horizon. So it all depends on you, the interpreter. You can do both in combination. Most of my interpretation projects, when I started to interpret seismic data, I would start with the major faults first, and then I will break out into the horizon interpretation, and then I'll go back in and fill in the smaller faults. Okay, that's what I felt comfortable with. And then you go into seismic attribute extraction, and all these things are button clicking. So when I started off working, people didn't call me a geophysicist, they called me a button clicker. Okay, so when you join the industry, they might call you a button clicker too.
So what is number 6? Can you explain it?
Seismic attribute extraction, it's just using the seismic data, right? Running a simple workflow to understand different things. And we'll comment it. We have a whole section in the talk about seismic attributes. Okay? And you try to put some sort of relationship to the attribute and geology. So you might be able to see the meandering of a channel or a point bar or something like of that nature, or a fan complex, things like that, but more in a visual or color display. All right, you'll see a couple of examples shortly. We have a lot of pictures in the lecture, so it's a lot of slides, but it's mostly visual. So let's move. Let's go on. All right, so what do you see here? Anybody? What is this?
Seismic.
Seismic, right? Good. Yeah. What type of view? Plan view. Well, right. Yeah, plan view. Yeah, but it's written there. It's a time slice. It's a time slice. You see down here? Time 920 milliseconds. So it's just a horizontal slice, right, of the data at 920 milliseconds down. Okay, so this is the survey boundaries, and these are could be interpreted as faults where you see my cursor moving through. Okay, those are some key little features there. Pretty good data quality, but you're looking at the data slicing through from on top. All right, so down if you go to the left here, you'll see the name of the seismic, PSDM. So it's a post-stack depth migrated full stack 32 megabit on scale seismic data. So it gives you a lot of information just by looking at the looking at the picture. All right, so this is what you'll be utilizing a lot in your career: time and depth seismic data. This is another view. So the next set of slides is basically showing you the different ways you can visualize the data to pan through the information. So this is just looking at data, another data set in a cube view. Okay, so you're looking at the data basically in a cube, but orientated in this view. All right, it's a 3D cube. Sorry about that. Our next data slides with some interpretation on. All right, it's an arbitrary line. Okay, an arbitrary line is just a point-to-point dissecting your data set, all right, with some interpretation here, as you see. So these are wells, these are horizons that you map, okay? So the what is this, magenta, what's this color? Purple, and the cyan, then you have the yellow, magenta, etc. These are all horizons of interest that they map, and these black lines are faults. That is interpreted. What type of faults are these that you could quickly say? What type of faults are these?
Normal fault.
Normal faults. Very good. So it's a very simple system to map, right? And scanning through the data again, you might have you have a cube of information now. So if you want to find out the information on this type of data, it's a coherency cube. A coherency is just a type of attribute that you get out of the data that you can take your original seismic data and generate this. You just take it through a workflow. And coherency is good for determining stratigraphic features and also structural features like faults and so on. Okay, so you see some sort of possible geological feature. All right, and then you have things like discontinuities or your faults. Okay, so again, it depends on what type of visual tool that you will use. You can dissect the seismic data in any way that you need to dissect it, to visualize it and to interpret it. Okay, provided you have your well data, you are now putting a seismic, as you're calling mapping. You're putting your interpretation, your spin, your opinion of the geology. That's what you're doing. Okay, but your opinion has to take into account the ground truth that is there, which is your seismic, not the seismic, but your well markers, your biostratigraphic data. All these things have to be able to tell the story. All right. And another view of coherency. All right, so it's the coherency data using the same two wells. Let's see, this one is at 13, 17. The other one was at 354. So this is pretty shallow, and then you move to the next one, which is pretty deeper down into the seismic. But you are seeing now a lot of nice faults here. Okay. All right. Another view again of seismic data. Showing you some markers and showing you a well with that doesn't have the labeling, but you have a wavelet here. You see this black wiggly line here? That's a wavelet. So this wavelet probably was derived from the well logs at this well location. Okay, so you could only get we may have to come out and, right, we have to come back out after this 10 minutes, right, and then come back in. So this wavelet is specifically for this set of well logs you have at this well location, okay? It's very easy to do. There's a program that does it. And again, once you have the well log information, you can generate a wavelet at that well location, okay? So you have this nice fault here, and this a nice normal fault. There are no rolls, so it's not a district, not district in nature. So this is down thrown, the up thrown side. So even here, if you have, you could possibly think about this as a possible area to drill, right? All right, and so this is the down thrown side to this fault here. So that's why they probably went after drilling on this flank of this fault. All right, so all these are well markers, your well logs, your wavelet, your faults, etc., etc. Let's go on. So what it's showing here is you can do simple things. You can do simple things to enhance your data quality. You're not a processor, but you're an interpreter. But an interpreter can also do some little routines in the software package that is available to enhance the data quality. So this specific routine here is called the envelope scaling. I think it's proprietary to Halliburton. And look at the process. The process routine takes you from the original data to the one on the right, which is pretty good and amazing in some regards too. We have a lot of now nice enhanced reflectors and stuff that you can see pretty good. So you can actually do an interpretation now on this. You can do it here, but the data quality is a little bit on the right. All right, so these are things that you can do on your own. Some other examples of improving seismic data quality, where you can actually now see what I interpreted as the erosional base of channel features, okay? And these are very important, right? Because these channels you have to think about scale and the potential for these channel features now to have reservoir in them. That is the whole idea of your interpretation. Putting your geological story and your geophysical interpretation now into sync, right? And then doing a quantitative methodology now to understand the reservoir. That is what you will be trained, or what you are trained or in training to do. Okay? Good. So so we mentioned about seismic attribute, Selena. So this is I can't see it, but this is probably there's a amplitude, an amplitude attribute generated here. If I probably zoom in into here, you might see the name of it. But just looking at it from experience, it's probably just amplitude. All right. So you're taking your seismic volume and creating an attribute volume in terms of RMS, root mean square amplitude, average amplitude, and so on. Okay. The one on the right is probably something called semblance or sweetness. These are just industry names that different vendors have. Okay. What do you notice here in this one on the right? What do you see? You see a little more what? At first glance, what do you see?
Vibrant colors.
Colors, yeah, but the colors have some sort of significance too, right? These colors are giving you some sort of stratigraphic detail, not so?
Yeah.
Right. So, yeah. Right. So it's giving you some sort of depositional story, not so? Where potentially you could have reservoir. Okay, you can have pay. And that is what you are trying to understand. So these are things that you could spit out in a second when you are doing your interpretation work. All right. Another example. All right. Let's go back there. Another example. A little more detail actually. So these two are shown very nicely here. We have a little more refinement, and you see some nice discontinuities, some nice faults are shown up. Okay, and then you have these stratigraphic things that you mentioned there, some crevice plays, some meandering channels, some, so it's pretty good. So these are just visual, but you have to put this in context of what you are trying to map. Okay, so you can get a lot out of the interpretation. And how do you interpret really? You do just, you take, so let's say this is your lease, this black area here, with some wells. All right, these yellow lines are basically like a polygon you use to define your interpretation. All right, and then these colored lines inside here, these horizontal and vertical lines are just seismic lines that you arbitrarily choose at a certain interval, and then you do interpretation on them. You do your horizon mapping, you do your, and this here is a fault. This one, in this polygon in the center here is a fault. So you'll interpret your horizon up to the fault. So this is just a polygon indicating a fault. And then where does the horizon go on this side of the fault, and where is it on this side of the fault? Okay. Are you all there?
Yeah, sir.
Okay.
So you could go over that.
Yeah, so this is just a snapshot of what a simple seismic interpretation grid will be like. Okay, so you do interpretations on lines and traces. So you can see here T stands for trace. Okay. L on this side stands for line. So this is line 100. So you will do an interpretation along this line. Okay. You can also do an interpretation along this trace. And if you notice, trace 300, sorry, that's 200. Is that a 2 or 3? I think it's 2. Trace 200 and trace 100 in the sec at this point here. So you can do this sort of intervals and do your interpretation based on your markers of interest that you are trying to interpret. Okay, so that's giving you an idea of the lateral or aerial extent of your horizon. That's what you're trying to do at a particular surface. So this is one surface that you're trying to map here. Okay, so it could be top of your forest, top of your cruise. All right. What was the reservoirs in Guyana? One? What's the main one?
I ain't sure.
Huh?
I ain't sure.
Yeah, sure.
No.
All right. Well, in Trinidad, the main stratigraphic markers are like your top of your forest, top of your cruise, top of your lower cruise, and so on. Then you have the river, you have the middle Miocene, and those type of things. All right. So you can do surfaces for each of those geological surfaces. Right? Horizon interpretation. So you just start with an interval. This is a color. This is a color bar. So this is you're using this color here. You're using basically a blue, red, white color scheme. So it all depends on, look at it, blue, white, red color scheme. It all depends on your preference. This is the well log, and with some markers, A sun, B sun, C sun, D sun, so on. So you could call them what you want. A seismic marker doesn't have to be a geological marker. And you just go ahead and you do your interpretation, which is picking a surface. So those are terms that you use, picking and mapping a surface. So this is a line. Okay, this yellow line in the center here. You decide to interpret this line with this color scheme.